Okay, cool. All right, morning, everyone. Really appreciate you for coming out. Thank you for being a part of this week's seminar. For those of you who do not know, for our guest today, I am Sadiq Perry, Academic Programs Coordinator here at the School of Environment. Again, thank you for coming out. Some quick housekeeping. As usual, make sure that you are on mute. And I say it every week. This is directed towards me as well, as I'm at home watching my kids today, and they can be very loud. But let's show our guest today much respect and make sure that we're muted. Only major announcement is that there is no session next week, so we're taking a break. I'm aware of Zoom fatigue, and everyone's in the Zoom several times a week. So I've had it spaced out in a way where we'll take a break next week and we'll come back. Excuse me, I'm trying to think of anything else. I think that's it. For those of you who have been asking about the recordings, they have been uploaded through our YouTube account. And so if you haven't gotten that email yet, just reach out to me or I'll send it out to everyone. But the sessions all the way through last semesters have been uploaded, so check that out. I know some of you need it for course related, for some classes. So today we have Dr. Breithaupt, and he's an assistant research and faculty member of the Coastal and Marine Laboratory at Florida State University. He has a BA in English from Wheaton College and an MS in Environmental Science and a PhD in Marine Science from University of South Florida, and has conducted research at the Florida Fish and Wildlife Conservation Commission and the University of Central Florida. The primary focus of his work is carbon and cycling of coastal environments. Please let's give Dr. Breithaupt let's do a digital welcome. Today, just welcome him. We're so grateful to have you. Thank you so much for doing this. So the floor is yours. We do ask if you have any questions, go ahead and you can put them in the chat and I'll ask at the end, or you can message me privately as well. But also I want to take a moment to thank, we have several guests from several of the schools. Thank you all so much for coming. If you have any questions about our programs, feel free to message me privately. I'll put my email in the chat as well. So I'll turn it over to you, Dr. Breithaupt. Thank you again for doing this.
All right. Thank you, Siddiqui. And thanks everybody for the opportunity to be here. I wish, I know we all look forward to post-COVID days when we can actually do this in person. But hopefully this will still be something that's informative. And I'm certainly looking forward to talk about some things that I really find very interesting. So just to make sure, Siddiqui, can you guys hear me okay?
Yes. Everything okay? Looks good. You sound good. Yes.
Okay, great. All right, so today I'm going to talk about this idea of the storm on the horizon, the vulnerability and the resilience of coastal wetlands to all sorts of global change. And before I really get started, I want to make sure that I mention this is obviously science is always a major collaborative effort. So there are many, many people who I'm not acknowledging here, but who have been very foundational and instrumental in a lot of this research. So don't look at this as a solo effort. There's many other people helping on this. The other thing I want to say is I'm focusing broadly on coastal wetlands, but today I'm really going to give most of my attention to mangroves. And there will be some mentions of salt marsh and seagrass as well, but the real focus is going to be on mangroves. All right. I thought maybe one of the best places to start is with a little bit of background so you know kind of who I am and where I'm coming from and why I'm actually interested in what I'm interested in. So I grew up overseas in Pakistan, and most of the time I lived up in the northern part of the country, up in the foothills of the Himalayas. But being in the Himalayas, come winter time, we would have so much snow that we basically would move down south. So we'd go down, spend a lot of the winters down in the coast. And this is a place called Hawke's Bay outside of Karachi. And you can see, this is me here strolling barefoot through the mud. And then some other adults here that are carrying this big green sea turtle that has crawled up over the sand dunes into the back barrier mud in the marsh on the backside here. And when she was totally lost and exhausted, this was about midday. So she's in the sun, she's stuck in the mud. And so the adults are doing all the work here, the heavy lifting, while the kids are just having fun. But this was a really foundational experience for me. It's kind of fun to look back on things and think about, how did this inform what I've chosen to do with my life? And so what's fun about this, I actually think, is there's this very charismatic turtle. And people think about marine science and they think about dolphins and turtles and whales and sharks and things. But really, what I focus on, what I'm interested in, are those things in the background and the things beneath my feet. So it's the mangroves. There's a big long patch running along the backside of this that are existing in this really harsh conditions, hypersaline, very high heat. And then really, as much as I love mangroves, really where I spend most of my time is looking at the stuff that poor turtle was stuck in. It's the mud and the sediments that are down below that. And so today I'm going to try to focus on a little bit of all of that. But the mud is where I got stuck in there too, as much as that turtle, I guess, and I still haven't left. So the goal today, I'm going to start out with a few slides, depending on the backgrounds of people here. I'm going to talk about what coastal wetlands are, sort of why they're so valuable, why I find them so interesting. And then I'm going to focus on sort of two different things. I'm going to spend a little bit of time talking about the vulnerabilities thing of these systems. So this is what I've in my title called the coming storm, the threats that are approaching these systems. But I'm really going to talk a lot about the resilience of these systems. And that's a lot of what I just find so fascinating. And then I'll finish up with some steps for moving forward in terms of where the research goes and sort of where we're at in terms of global interest in coastal wetlands. All right. So the big thing to be aware of is that coastal wetlands just provide this wealth of ecosystem services for us. And it actually gets quite difficult to account for them or put a dollar value on them because there's so many things associated with it. So one of them, this is a lovely publication that just came out the end of last year, but basically just talking about there's all sorts of reasons that people value these ecosystems, but wildlife is one of those that's really charismatic, right? You can get it in photos. And so there's globally, there's all these just amazing organisms from micro to macro that can be found in mangroves and marshes. And so just a couple pictures here that are kind of amazing, right? You've got mud skippers, you've got all sorts of different kinds of birds. There's birds in Latin America, South America, tigers in India, and the saltwater crocodiles, which obviously make things a whole lot less pleasant when you're there, a little bit more terrifying. Fish, though, are the piece of things that are really interesting because there's so many fish that spend some part of their life stage in coastal wetlands. And so any threat to wetlands is a threat to these different fish. And this gets to the difficulty of accounting for their value because these fish obviously travel all over the world. And so fisheries are dependent on coastal wetlands far beyond the scope or the square footprint of what those wetlands actually occupy. So, okay, the animals are one big thing, why these are really valuable. The second, though, is this little graph that basically shows how when you have a wetland, in this case, particularly a mangrove wetland, it can suppress storm surge. So when a hurricane comes ashore, it's not just the wind we have to worry about, right? It's the waves and the way that sort of pushes up the water in on the coastal community. And so across this x-axis, you have the width of mangrove communities. So this is in kilometers. And then as you look at sort of the y-axis on your left, that's related to these profiles here, like the red, green, blue, and black. And you're basically saying that for every kilometer of mangrove width, it's suppressing that surge so that by the time you have 7 or 8 kilometers of mangroves in front of your communities, you're suppressing that storm surge by 70, 80, 90%. And so there's a lesson here, basically, instead of mowing down all the coastal wetlands and putting up our hotels and condominiums right where they can see the water, if we set them back behind the wetlands, that infrastructure we're building is going to be a lot more resilient to things like storms. And then this final point here is getting to the idea of carbon sequestration in these wetlands. And honestly, it's this piece of it that has really given so much attention to coastal wetlands in the last decade. There's always been interest in the animals that, you can find research going back a long time, couple of centuries actually, in terms of sort of what's going on in mangroves. People have always been interested, but in terms of this global effort and around this, what we're calling blue carbon, it has to do with how much carbon is being pulled out of the atmosphere and sequestered in the soils and the plants of these systems. And so this plot just gives you This is in log scale, by the way. This is carbon burial, so grams of carbon per meter square per year. This is salt marshes, mangroves, and seagrasses. So you can see it's like order of magnitude greater than these other ecosystems, tropical forests, boreal forests, and temperate forests that we think of as such important carbon sinks. There's no comparison in terms of what these coastal ecosystems are doing for sequestration of carbon. And so I want to just for a second then sort of talk a little bit about some operational definitions that I'm going to be talking about through the rest of this talk. And one of the things we're going to use is the phrase a stock of carbon. And so a stock of carbon is sort of like your bank account, like what's your balance? How much do you actually have? And so a stock of carbon, in this case, it just basically ties to the ruler, how deep your soil profile is. So how much carbon is in that soil. What I focus on a lot, though, has to do with dating. So if I use radiometric isotopes, I use some other manual methods too, where we use some marker horizons with a known date, and we can measure how things change over time. And what's nice, as soon as you can add dates to your soil profile, you can actually now start to calculate rates of change. And so one term I'm going to use throughout this talk is accretion. And accretion is just this idea of the vertical, the change in the height of the soil. So in this case, we have 5 centimeters that's accumulated in 10 years. And so you just do the math, 50 divided by 10, you have 5 millimeters a year is the average rate that soil is being added over that specific window. Now, that's just, again, it's just a ruler at that point and dates. But what we're also going to talk about, and I'm going to spend a lot of time talking about, is burial. And this is now where we're adding a mass term. So we're using bulk density to understand the mass per unit area, and then again per unit time, so over 10 years. So I can calculate a burial flux, in this case, a kilogram of sediment per meter square per year. What's handy about that then is that gives me my total flux for all the sediments. And so then if I know my representative fractions for these other materials that I might be interested in, so whether it's organic matter, mineral sediment, the carbonate fraction, organic carbon, nutrients, or lignin, or some other kind of other biomarker, as long as I know how much that represents of the total soil profile, I can calculate a burial rate for each of those things as well. And time is really important. You know, if you think about what global change means, we're talking about how things are changing now faster than they have in the past. So it's very important that we have a historical context and rates of change to be able to identify how quickly things are happening and the mechanisms that are making that happen. And this is a figure that I put together actually a long time ago for my master's thesis. And I share this with you because I found it very helpful. So it's basically a very simple box model describing how carbon moves through a wetland. Again, this time focusing mostly on a mangrove, but you're basically starting out with CO2 in the atmosphere. It's moving to the mangroves or the biosphere. As those die, it gets transported to the soil where it can be sequestered under the water because the water's rising. It's anaerobic conditions. The microbes can't break down that organic matter as much. And then there continues to be exchange between the sediment and either the river or the ocean that's next to that particular mangrove. And what I want to just point out is that the boxes basically represent pools. So that's the bank accounts, how much is in each different account here. And the arrows are representing fluxes. So how much, in this case, carbon is moving between each of those pools over time. And I want to show you, this is a figure that just kind of gives you a sense for how dynamic that is. So this was a chapter that I put together in my master's thesis, and we published shortly thereafter, basically just identifying globally of all the carbon that is fixed into mangroves in particular, about 12% of that would be buried over a long time scale. But look at how dynamic the rest of it is, right? There's a lot of it that's just respiring right back to the atmosphere as CO2. And there's a lot of it that goes out as dissolved inorganic carbon, dissolved organic carbon, or particulate organic carbon out to the nearby aquatic environment. So it's very dynamic. It's not something that's as static, except for that carbon that's stored in the soils. And this is what's kind of important. So this is a really important paper that just came out last year, looking at carbon stocks all across mangroves all around the world. And I do want to point out, it is kind of ironic, you know, we call it blue carbon, and it's been a very charismatic term that a lot of people have really gotten behind. But if you look at this profile and you look at these soil cores, it's much more brown in appearance. It's not blue. In fact, when you have a lot of carbon, the water tends not to be blue. So it's kind of funny that blue carbon as a name has taken off as well as it has. But the thing I want to emphasize in this figure, you don't necessarily even really have to worry about the numbers as much as just the relationship of green to brown. The green is indicating the above ground biomass, and the brown is everything that's in the top meter of soil below that. And you can just see, this is what we see everywhere in these systems. The amount of carbon that's stored in the soil far surpasses that in the biomass and even the stuff that's being sent off. It's the soil stocks of carbon that are really important. And one of the things I would just point out actually too, if you look at these soil cores I have on the side, these pictures, they're all from different mangroves, and you can see they're very different in their appearance. So there's different carbon densities in these soils, and that's why there's this global effort to go out and take cores and mangroves all over the world and understand how much carbon is actually there, so we understand sort of what the vulnerabilities are to global change. I also want to take some time here and just mention that the focus of blue carbon really is on organic carbon. And by organic carbon, I mean any of the carbon that's incorporated in these photosynthetically derived organisms. So plant biomass, basically, and after it's died. And the thing that's important about organic carbon is it's directly pulling CO2 out of the atmosphere and fixing it in these vegetation forms. And so if you look at the little equation here at the bottom, you can see it's pulling down CO2 plus water. This is, the old photosynthetic equation, producing some sort of organic matter and releasing oxygen. This is really basic, but I want to contrast that with what happens with inorganic carbon, because it's very different and it makes things kind of complicated. And I'm not going to talk about this a lot in the talk, but it is something that's really important to be aware of. So things like corals and all sorts of bivalves and things that all these organisms in the ocean that use calcium carbonate as part of their skeletal supporting structure. When they're doing that process, you're taking calcium and bicarbonate and you're forming calcium carbonate. So that's the basis. And in that process, you actually release a CO2. And so the point here is it's opposite in terms of what it's doing for greenhouse gas sequestration. So as you form all this kind of material that's made out of carbonate, you're actually releasing CO2. And if you dissolve that material, you can actually pull down CO2. So it's a little bit counterintuitive, but it's something that's really important to keep in mind. Okay, I want to mention here something that's kind of important, because we tend to get sort of looking at things on human timescales and what's happening recently, but halophytes, so these are plants that are very well adapted to living in salty conditions. This can include marshes and seagrasses and mangroves. They've been on coastlines on this planet for millions and millions of years. And it's important to remember that. But this is one paper that I think is particularly fun to draw attention to. This is already now 20 years old, which is kind of surprising, but this is from a dig about 300 kilometers from the Mediterranean coast on the northern edge of Egypt. And so this oasis where this dinosaur was dug up about 90 to 100 million years ago was at the coast. And so this paper specifically talks about finding this large, it's called a paralotitan. At the time was the largest dinosaur that had been found in the world. It was found in this mangrove environment. And so I just think it's kind of cool to be thinking about mangroves being around for this long a period of time. And everything back in that time period was much larger. So even just imagining the mangroves as these much more gigantic coastal vegetation, the dinosaur would kind of wander around and scavenge on, much like a lot of herbivores do today. So if we know mangroves have been around for a long, long time, and they've obviously dealt with certain kinds of cataclysmic change over that time period, the question is, what's happening now? Why are we so concerned, and where's all this vulnerability coming from? So this now moves me to the second part of the talk, where I'm going to talk about vulnerabilities. And I had a geology professor in grad school who had this signature on his email, and he would always talk about the idea if there's no rocks, no water, no ecosystem. So he was a geologist. But I think that the same thing applies when you talk about wetlands, because what happens here is if you have no plants, you lose the soil, and you lose the plants in the soil, you lose the ecosystem. All of the services associated with that are also gone. And so this is a figure just showing mangroves and marshes and these different stressors that can impact the health of the plant. This ranges from acute things, including hurricanes, the surge that comes with hurricanes, fires, and then these chronic things, which means that they're sort of things that are just slowly happening and pushing against the wetland. And so you have hydrologic alteration, where we're changing how water flows through these environments. Nutrient loading, where we're adding much more out to the coast, and so they have to adapt and deal differently or compete differently for resources. And then sea level rise is really the big one. And so we're going to talk about, to some extent, we're going to talk about all of these today, except for fire. And so getting to this idea of like what's different now, it's really the idea of loss, and it really is loss driven by humans. And this is something that, you know, we've been coming to terms with. And if you look at mangroves, this is again from a foundational blue carbon paper that came out 10 years ago now. But mangroves, if you look at them, we've lost about 20% since the 1980s, and anywhere from 30 to 50% since the 1940s. Seagrasses, we've lost 50% since the 90s. That's a 20-year period. The seagrasses are just wiped out. And salt marshes, this idea is 25% or so since the 1800s. And this mapping is getting much, much better as we have a lot better tools like remote sensing to help assess this now. And I'll show a little bit more of that at the end of the talk. But the idea is there's really substantial loss occurring in these coastal systems. And this is actually sort of a really cool paper that came out last year. Oops, sorry. Looking at different regions of the globe and the reasons for loss. And so I just want to point out a few things. So see here, this box right here, the color coding represents the Caribbean mangroves. And green represents extreme weather events, and blue represents erosion. So these are basically, they're largely natural causes for the amount of loss that's happening in the Caribbean. If you go into like coastal Africa, the mangroves in that region, you'll notice yellow is much bigger here than it is in any other region. This basically has to do with like petroleum extracts. You're doing non-productive conversion, so you're not changing it to something else that draws down CO2. And then this area here of South Asia, where you see all the orange, what's happening in this area is all these kind of conversion to things like rice paddies, shrimp farming, and like oil palm plantations. And so there's very different drivers in different parts of the world as to what's causing loss. And that helps us sort of know better how to tackle, how to preserve and maybe mitigate some of that impact. Great, so in terms of these natural drivers of vulnerability or natural drivers of damage in these systems, one of the big ones to think about is hurricanes. And we saw in that previous graph that that's a big driver in the Caribbean. These are just figures basically of Hurricane Wilma in 2005 and Hurricane Irma, or sorry, actually this isn't Irma, this is, I got the wrong one there. That's not even, all right, I don't know which storm that is. That's a bad image. Regardless, these happen across the Gulf, right? So this picture here, this is from a paper came out a couple of years ago, just plotting the paths and the size of storms across South Florida. And you can see Hurricane Andrew, if you remember that from '92. There's the Labor Day storm of 1935, which was catastrophic for the Keys. And then even other things like Irma and Wilma, storms that have occurred in the last 15 to 20 years, causing really interesting changes in the South Florida landscape. And so what I want to point out from that, this is a map showing storm surge. And I've drawn an arrow to this purple section of Everglades National Park, where I'm going to show some data in the coming slides. This is where you had 6 to 10 feet of storm surge. That means the water was 6 to 10 feet above what the usual tidal stage was in those areas. This is what that actually looks like then, what the damage ends up looking like. So on the left, you have a mangrove in 2017 in that same area. If you go back just shortly thereafter, because Irma occurred in September. and just look at the damage that's there. It's completely defoliated. A lot of trees have actually been knocked down. And then this is a picture down on the bottom right of what the storm surge does when it brings in marine sediment and piles it on top of the mangroves. And what's really interesting in this plot, this is from some colleagues at Fish and Wildlife Commission. If you look at the storm deposit thickness, so in this case, if you look at how much mud was added to these different places that are being monitored, tree mortality doesn't really change across minimal to moderate thickness. But what started to become interesting is for when you have thick deposits of mud, it doesn't even really show up in the mortality in the short term, but it's the long term. So over the 9 months after the storm occurred, you're starting to see tree mortality that's on the scale of 40 to 50%. So it's really interesting to see how mud can have this very slow kind of suffocating effect on the mangroves. The other thing I just want to mention, though, is sometimes the storms, it doesn't necessarily matter exactly where that thing comes ashore. In this case, there was very high storm surge, even 3 to 5 feet up here in northeastern Florida. And I happened to be at University of Central Florida at the time, and we were out doing basically rack deposition surveys that whole year. And what's fascinating is just to notice, like when Irma came ashore, it's just a totally aseasonal, very large pickup of rack. So in this case, almost all of it was seagrass. And so there's very significant damage to those seagrass ecosystems, but there's also an impact that occurs to those coastal communities that are now buried under all these large mats of seagrass. I want to talk about this one as well. This is one of the things we talk about with wetlands, is getting the hydrology right. This picture is from a place it's in Naples in South Florida. And there are these two major die-offs of mangroves. That one is 20 hectares, this one's 20 hectares, this one's about 4 hectares in size. And basically these things both occurred coinciding with the installation of these roads. These roads are there to facilitate these large condominiums and boat ramps that we put in so that we can get out to the coast, right? But what happens as soon as we put those roads in is it stops the tidal exchange. So now the water gets in there and it's just stagnant and salty, and you build up sulfides. And the plants, while they're very well suited to handle these kind of conditions for certain periods of time, after a few years go by, you can see this, what we're calling the ghost forest of South Florida at this point. The trees die. And then you try walking through this environment, the soil structure starts to collapse as well. And so you really do have a collapse of the ecosystem. The other thing I'll just finish this with, though, is to restore this is actually really easy. All you got to do is restore the hydrology, and this system will restore itself. I say easy, though, because that's not exactly true, because these are, state roads, and getting the permitting and the funding just to put culverts under those roads is a multi-year, major funding problem. But in terms of what we need to do, it's actually quite simple and straightforward. I'm going to finish this section talking about vulnerabilities, just talking about sea level rise. Because sea level rise is one of those things that's like a slow and steady press, and you don't necessarily see the impacts of that right away. And so here, and this is from some research I'm going to talk about in a little bit more detail in some upcoming slides, but this is both for South Florida and the Yucatan Peninsula, where the blue represents the vertical accretion of the soils in these wetlands. And then the orange represents relative sea level rise as monitored by a local tide gauge. The thing that's interesting to notice here is over 100-year timescales and 50-year average timescales. There's no difference in South Florida between the rates of accretion and sea level rise. They're marching in lockstep. It's great. The problem is this most recent 10-year period, you see sea level rise really accelerating, and you don't see that in the pickup in the accretion for the wetlands. And so as of yet, there's no catastrophic loss happening to these wetlands, but you start to wonder, to what extent can this relationship be maintained, and at what point is there a tipping point reached where the mangroves can't respond anymore? The Yucatan, the problem is that the sea level rise data was a little bit more sparse, but even the same thing over that 50-year time scale, when we did have data available, very different. There's a discrepancy, right? The accretion is not matching up with what sea level rise should be. Or sorry, it's not matching up with what the sea level rise demands are asking of accretion. All right, so I really don't want this talk to be a downer or a negative one. There's a lot of things I want to focus on today that are about the resilience of these wetlands. And that's the thing that I think when you get a chance to get out in some of these places and just realize how amazing they are, how vibrant they are, even in these very stressful conditions, it's pretty amazing. So I want to talk a lot in this upcoming section, sort of what that means for this section right below the forest or right below the marsh, where the sediment is accumulating and how resilience is exhibited through those processes. I'm going to preface this all with a quote here from Colin Woodruff, who's a coastal geomorphologist from Australia. And he's written some textbooks and many, many amazing papers. And this is from one of his papers in the early 90s, saying that the carbonate settings in places where the sedimentation is predominantly autochthonous. So this means places where sediment is largely locally produced. That might be carbonate material, or it might be the organic material produced from the vegetation. In those kind of settings, they're much less likely to be able to keep pace with sea level rise than allochthonous settings where large volumes of sediment are transported in. So a good example of this would be places like the Mississippi, or even up here in Apalachicola, where there's a lot of terrigenous sediments transported by the rivers, and that helps these places keep pace with sea level rise. So in some ways, I treat this as a hypothesis, because he's saying that carbonate settings aren't going to be able to accrete as much as some of the other settings. And so I'm going to be talking in the upcoming slides about data sets that come from Southwest Florida, as well as both sides of the Yucatan Peninsula. And also, just for reference, for my Everglades data sets, I'm talking about the Shark River, which is this long transect, which is the primary way that water gets out of the Everglades. Something like 90% of the water in the Everglades comes out of the Shark River. And then the Harney River and the Broad River just north of that. Okay, so I talked about storms and the damage they can cause, but I don't want it to be just a one-sided story, because as often in ecosystems, it depends, it's a matter of degrees, right? So Irma, while it was very destructive in some places, in other places actually deposited this very thick mat of sediment. It was actually very useful. So if we think about accretion, this is actually a very helpful thing, right? It added about anywhere from 3 to 4.5 centimeters of sediment in a single event, whereas usually they're doing 2 to 3 millimeters a year. So we're talking 20 to 30 times the amount of sediment deposited in a single event. So from an accretion standpoint, that's great. It's a really helpful subsidy. The other thing that's really fun to look at is the content, or what this storm material is actually made of. And the really important thing to take away from it is that total phosphorus is very, very high in that storm material. This is particularly important in carbonate-based systems that are phosphorus limited. So the Everglades is very phosphorus limited. And so you basically have these storms taking in a lot of the limiting nutrient. And so it helps with accretion, and it helps with nutrient supply for the vegetation. Because it's storm derived, all that material that I just showed in that previous picture, if you look at each of these sites, so I mentioned these 3 rivers, the Broad River, the Harney River, and the Shark in the Everglades, what you can see, these bars that are on your left represent the coastal sites. And so salinity is increasing from right to left. And you can see that the carbonate deposition is orders of magnitude higher at the coast, right? That's the storms. This is bringing this in. And I should mention, it's not just hurricanes, it's also frontal storms that come through in the winter that bring in material just constantly. And so this leads to this hypothesis that actually a number of people have raised, which is that storms and the delivery of this sediment are actually going to help these sites keep up with sea level rise. And so what's cool is we have this big data set from all these different sites where we can actually look at that hypothesis. Is the more massive sediment you add to a site going to actually help it keep up with sea level rise in a better way? Each one of these is 100-year averages of organic matter accumulation, mineral sediment accumulation, and then just accretion. So if more mass is going to help these places keep up with sea level rise, then you should be able to add the organic matter and the inorganic matter and see that there's a greater accretion rate. So let's just take 2 examples here. They both have about the same amount of organic matter being added to them. But the inorganic matter is very, very different, right? This one here, we're about 1,700 grams per meter square per year. This one here is about 300, 400. So if you add those two together, you would expect the accretion rate to be much, much higher if the hypothesis of sediment mass being delivered to these things holds true. You can see here, it doesn't. So why is that? Well, we put these things together. If you look at soil, there's only two basic components you can have: organic matter or mineral sediment. There's also water and gas in there, but those don't really contribute to actual mass of the sediment because we usually subtract those out. So if you take those two terms, we looked at sort of three different classes of sediment. We used organic sites, intermediate sites, and mineral sites. And just keep in mind, the mineral sites are basically those ones that are closest to the coast that are getting all that carbonate mineral sediment delivered to them. If you first look at the coefficient for this organic matter, so this is basically saying how important is organic matter to accretion in these sites. I'm going to argue that these are basically the same number. The intermediate sites have a number that's a little bit higher, but what you keep in mind when you compare it to inorganic matter, the mineral sediment, this is changing by a couple orders of magnitude from the organic sites to the mineral sites. And so what's interesting to take away from this is even in these mineral heavy sites, though, the coefficient that tells you how important it is very, very small. So it's saying the more, and the fact that it changes from large to small is telling you that the more mineral sediment you get, the less it's impacting accretion. So why is that? Okay, so this is where having kids and a youthful spirit is helpful, because here's a metaphor that I think actually helps us explain this pretty well. I'm going to treat Lego as mineral sediment, and I'm going to treat this Nerf ball as organic matter. And if you treat both of them on their own as additive materials, what that means is for every extra Lego block I add, in other words, if I double my number of blocks, double my volume, I've also doubled my mass. Same thing with the Nerf balls. If I have one ball and I double that, my volume and my mass have doubled. It's a conservative relationship. The complicating factor with the soil building is the fact that they're interactive, right? So you think about, like, if you go to McDonald's and there's this big ball pit full of all these balls, and then you start taking a handful of Lego and dropping it in there. The mineral sediment can actually fill in all the pore space in between that the organic matter has in between it. The other thing you can think about is if that Lego actually gets built together as sort of a big block, and now you put it on top of those foam Nerf balls, it's actually going to compact and compress that material. So this is why you can't just add more mass and expect the same change in volume or accretion for those sediments. And this shows up really well when you actually try to explain this mathematically as well. So that the inorganic matter, there's this very tight relationship with the bulk density. So how dense is your soil or your sediment? Basically it just says the more mineral sediment you add, the denser your material gets. Whereas organic matter is very variable. It has very little predictive capacity for telling you what's happening to bulk density. Conversely, when you look at accretion though, organic matter, this is the Nerf balls, are doing a really good job of telling you how much accretion is happening because it's able to expand and contract, right? The bottom plot showing mineral sediment, it's important. It still has a predictive capacity of about 20% or so. It is making a difference, but it's not nearly as helpful in explaining things as accretion or as organic matter. Just to finish this section up then, so if we have that understanding of what kind of needs we have for both mineral sediment and organic sediment, you can look at what future sea level rise is going to look like. And so this is basically the blue lines in each one of these represents the low end estimate of about 9 inches of sea level rise by 2060. The red lines represent 2 feet of sea level rise by 2060. And what you can see, the dots just represent different ages of soil, of mineral and organic material that we've seen in the past 100 years. And you can see that we have evidence to see that we can probably see places that will keep up with that 9 inches of sea level rise by 2060. We have zero evidence that there's one data point that it's going to work if we start approaching two feet by 2060. And I should mention that this is linearized over that 40 to 50 year time scale. So if sea level actually starts to accelerate more than that, then all of our past scenarios aren't really going to be very helpful for predicting this. But I would say what we tend to get from this, going back to Colin Woodruff's hypothesis about whether carbonate settings are going to be more vulnerable than others, we do seem to see that it's the sites that get that material from outside the system that do have a little bit more ability to keep up with sea level rise. Okay, so in this next section, I want to shift gears just a little bit and get into some chemistry a little bit more. And this is the idea that maybe the past isn't necessarily going to be our best predictor for looking at vulnerability and resilience in the coming years. This is a study that we did across mangroves and marshes of Southwest Florida and a bunch of mangroves kind of up around the bend of Rookery Bay and Naples. And what I would mention is that we have one site where the marsh is about 220 meters inland. So there's a mangrove fringe of 220 meters thick. And then another where the mangrove fringe is only about 40 meters thick before you get to like more of a juncus marsh on the backside. We're exploring a question here that's really interesting, and it's been in the literature actually in a number of different ways. But if you go out and measure burial rates of carbon and you put those over time, what you tend to see are these increases, that it looks like carbon burial has actually increased over the past 100 to 120 years. And this is our data set, but this is not unique to us. This has been found in salt marshes and coastal sediments kind of all over the place. This does have a tectonic dependence. This isn't so much in Australia, but certainly in North America and Europe, this has been seen. And so the question is, what drives this appearance of an increase? And really, if you think about it, there's kind of three things that can do this. One is that there's some effect of the dating tools that you're using that are doing this. The other is that there's some sort of post-depositional change. And that's kind of a funky term, but I want to explain what I mean by that. So post-depositional change would be, if I'm depositing organic carbon at the surface in these settings now, over the course of 100 years, it's going to get degraded by the microbes, it's going to get dissolved, leached out. And so maybe what happens is it just looks like a decrease because the material that's deposited here at the surface is just being degraded over the course of 120 years. That's this post-depositional change. The third alternative, if you eliminate those first two, is that this is a real increase. And then you get to the question of how you explain how that is happening. So that's what we set out to do. So in this slide, I'm not going to go into a lot of details on these methods, but basically we compare our dating method to a couple different methods and find out there's pretty good agreement. If you start trying to parse them apart, the differences aren't enough to drive an actual acceleration profile. So it's not a difference in methods that's doing it. And I would also argue that this is from another paper where this is again from sort of this part of the Yucatan Peninsula where a bridge was installed across a lagoon. And you can see that the dating method actually does a really good job of picking up change that occurs over time. In this case, it picked up an increase and then a decrease. And this is pretty well known in the sort of the paleo work where you're trying to reconstruct how things have changed over time, that this method works pretty well. So it's not dating. That's not what's driving that appearance. Getting at the idea of post-depositional change is a little bit more complicated though. And this is where we're trying to use some proxies to try to understand what that might look like. So these are two, I want to make clear, these are just conceptual models at this point. This is just trying to think about how we would get at identifying post-depositional change. And we're using lignin, which is a component of organic matter that is very resistant to degradation. There's almost no degradation that occurs in anoxic environments. So it's very useful for looking at wetlands environments where they're largely anoxic below the first couple centimeters. So if I was looking for a degradation profile, if I wanted to say it was post-depositional change that is driving these profiles, I would expect that lignin basically is going to stay the same from top to bottom in my core. Whereas the total organic carbon pool that's going to change over time, I would expect that this is just what a degradation profile is going to look like. It's going to be high at the surface and degrade at depth. Conversely, if I actually want to say that it's an acceleration profile, I would expect that as carbon, that total carbon pool is increasing, the total lignin pool should increase in lockstep with it. And so if you look at this in terms of ratios, a degradation profile should actually have this kind of negative slope so that the ratio is increasing with depth. So lignin is going to stay there. The other carbon at depth is going to be degraded. And so that ratio is going to be greater at depth. Conversely, if I want an acceleration profile, what I'm actually looking for is pretty straightforward. I want just this basic vertical line that says, as carbon increases or decreases, lignin increases or decreases with it. So keep that in mind then. This is what our ratios look like for each of these cores. And for the most part, they're all straight on vertical. There are some changes. This one kind of has a couple spots that might be a little bit out, but the slope isn't significant. There's, so it's not driving this profile. And certainly look at some of these other ones that are they're dead on vertical. If anything, that some of these sort of have maybe a little bit of a positive slope, which actually says that you're actually getting sort of a change in source, maybe to a more woody kind of material, maybe from a marsh to a mangrove transition. So this really, the takeaway from this, we used some other lignin biomarkers with this as well that I'm not going to talk as much about. But basically the idea here is there's degradation happening in these soils, but it's happening uniformly to that material. So at a certain point, once it's been buried, there's not further degradation happening to it over time. And so we're left with the conclusion that it is a real burial signal. And in this case, we want to try to understand like maybe how this is happening. In this case, I've got a core that's about 4.5 meters deep of peat. This is in South Florida. And if you measure accretion, so you're taking depth divided by time, it's about a little bit less than a millimeter a year, 0.9 millimeters a year. And if you look at sea level rise over that corresponding time scale where that peat has accumulated, it's almost the exact same, 0.7 plus or minus 0.3 millimeters a year. So basically there's this very strong indication that sea level rise controls carbon burial and accretion over these long time scales. What's happened recently though, in the past century, sea level rise has bumped up. It's about 3.5 times greater than what it was in the past. And even if you zoom in on sort of this part here right at the very end, this is where you're getting to the 6 or 7 millimeters a year that we've started seeing recently in South Florida. So there's a strong relationship between sea level rise and what's happening with carbon burial. I also want to just sort of point out this very quickly as another potential mechanism. So I've talked about this carbonate layer that the storms deliver. It's very thick and very dense, and I've shown earlier that it's capable of actually suffocating the plants over long time scales. What's kind of cool is it's actually able to, when you put it on top of a peat soil, it actually suppresses the flux of CO2. It suppresses microbial activity so that that underlying organic matter doesn't get respired as much as it would have without that material. And so there's a potential that these storms are doing all sorts of things. It's not just one thing. There's all sorts of different things that they do to help preserve carbon, add carbon, change the life expectancy of the plants. All these are dynamic things we have to account for. All right, so I know I'm getting short on time here. One of the things I wanted to talk about as we finish is just that there is actually good news for us to think about. Focus on the plot actually on the right, not so much the one on the left, just in the interest of time. The size of these bars represents the causes of loss. Red meaning people have caused the loss, blue meaning it's a natural process like storms or sea level rise or something like that. What you can see over the last 20 years. So from 2000 to 2005, the magnitude of these losses was much higher and has been decreasing very steadily. So this is a really important paper that came out last year, this massive remote sensing effort that's actually giving us some good news that the rate of loss is decreasing. We are making a difference in preserving and taking care of these environments. So what's cool about that as well is that we can actually be very successful with restoration. So the blue bar, just focus on this one, is for mangrove restoration. More so than any of our other upland places, is very, very capable of restoring carbon stocks to these locations. And so that's good news. That's something we can work with. But it's prompted projects and questions like this that say, can we manage these coastal ecosystems to sequester more organic carbon? And the question I'm asking is actually, is this a good idea? Because ecosystems have lots of services and things that they're balancing. And so for us to choose to identify just one process, carbon sequestration, and focus on that, we need to understand what the trade-offs might be. And so one example of this, and this will be kind of the last thing I talk about, is just oyster reefs. Oyster reefs are in decline all over the world. And one of the things that's just come out in a recent paper is this idea that mangroves with climate change are actually moving onto oyster reefs and setting up camp. And if you look over time, this is a time series of historical aerial photographs showing mangroves moving on since 1943 up to the present. And you can see them expanding dramatically on these oyster reefs. This was work that was done over in the Indian River Lagoon. And so what's interesting, I've had a chance to work with these folks, and we've been out burying oyster shell, burying oyster shell on reefs that have mangroves and some that don't have mangroves. And what you can see on the plots on the left, this top is a mangrove encroached reef. And you can see that oyster shell is dissolving substantially faster. This is over about 325 days. This is preliminary data that we're in the process of gathering. So anywhere from 4 to 5% mass loss in those shells buried under mangroves compared to the controls that are buried on just a regular oyster reef. And basically what we're looking at, and we're probing this in a number of ways, but as the mangrove roots grow down and litter gets involved here, you're introducing all sorts of just sort of natural exudates that are very acidic, like nitric acid and carbonic acid, that can create a very unstable relationship for the oyster shell. So again, we have to be careful. Just maximizing organic carbon in these systems may not be good for oyster reefs and all the things that are associated with their services. All right, so I apologize, I think on time I'm running maybe just a little long. I just want to finish up with 3 key takeaway points. So I know I've talked about a lot, but if you can remember these 3 things from my talk, I feel like I've been successful. The biggest thing would be to think about in terms of carbon. The greenhouse gas component is very, very important. But I would also ask you to remember that carbon is actually a soil building block. When you think about those Nerf balls, so when you think about carbon, think about Nerf balls. It's very, very effective at helping build soil and help these wetlands keep up with sea level rise. The other thing with sea level rise is to remember it's been occurring for millions of years. Sea level change has been occurring, and these wetlands have existed with them. So sea level rise in itself is not a bad thing. The thing that's in question is the acceleration in sea level rise. That's what we don't know. The tipping point at some point is going to occur, and these wetlands aren't going to be able to keep up. And then the same thing with hurricanes. They can be really destructive, but they've also got a lot of really helpful things that they do for wetlands. And again, it's all kind of in a balance of perspectives. And so with that, there's lots of funding, lots of people that have been a part of sort of all these different projects. And I'd like to make sure I give a shout out to those. And then at this point, I'd love to take questions if anything's coming on the chat, or if people want to jump in over the mic, that'd be great. Thank you guys. I appreciate the opportunity.
Well, thank you for that. Really appreciate it. I'll start. When I got privately, just said, can you share your big change from English major to science, and what was the driver?
What was the driver? Okay, so I've always loved outdoors, right? And that's been a big part of who I am. Literature, I think, for me was a way of just sort of figuring out. It's a life process, trying to figure out sort of who I am, how I fit in with things. For me, a very important writer was Salman Rushdie. He's got a lot of in his writing about being a third culture kid. So somebody who was born in South Asia, raised in England, and then talks about sort of you don't really have a home in either place. So that was, for me, literature was very important in that regard. But then, the outdoors kept calling, and I had my opportunity to get my feet back in the mud, and I haven't left since then.
Cool, thank you. So we'll open up the floor, so to speak. Anyone has any questions?
So thank you for your talk, Josh. Could you go back to your slide where you were showing the lignin profiles?
Yeah.
And I mean, we teach here stats to our students, and always make sure that your R squares are close to 1 and X, Y, and Z. And I noticed that your R squares, they're different, of course. So how could you statistically relate to that, given that they're not even close to?
Right. So what you actually want in this case, thank you. It's a great question. What you actually want in this case is an R square means that there's no trend, right? That lignin, the depth is not explaining that. And so you actually want low R squares. There's a couple places where it gets marginally strong. Like here, you could argue that there may be a little bit of a significant relationship, or at least it may be fitting that. But then when you look at the p-values, it's not a significant slope. So it's putting those two things together, trying to evaluate, is this a significant slope in what's occurring here?
Mhm.
Does that make sense?
Yep. Oh, it does to me.
Okay, okay.
I have a comment more so than a question, but
Sure.
your discussion of that road and how it was apparently killing off, I guess the mangrove section.
Yeah.
Pretty thought to me, because I guess that's saying that it seems to imply that the surface water is probably having more of an impact than the groundwater. And I was figuring that maybe the groundwater would have even more impact. I need to rethink that. But another thing that the thought that was created is, if we know that building a road along the coastline can impact wetland this way, then that ought to be a part of our environmental impact assessment. And apparently we are not considering that at all.
Right.
So anyway, as I said, it's not a question, it's a comment. It just created a lot of thought in me. Thank you.
Yeah, absolutely. No, I appreciate the comment. So, I didn't talk about groundwater really at all today. And that's really, boy, it's a major force for change in terms of a lot of the export. So, but I think, yes, you're exactly right. They're both very important. But what's interesting is when you take the stuff out and you allow at least the surface water to make some exchange, then it allows a better balance between, it's not this massive buildup of the sulfides in the pore water that can be so stressful. So yeah, they're both very important.
Okay, thank you.
So I follow up on that, Joshua. I mean, you have some mangrove forests that you do have an actual, riverine freshwater input, but then you have other mangroves that are strictly groundwater fed. Does that difference in water source plays a role in carbon burial at all?
Sure, it could. I mean, one of the things, so if you think about, I mean, that's a really fun conversation to think about. So there's places, so for instance, in the Yucatan, where the Petens well up with this groundwater, you can look across the landscape and you can basically see, it looks like there's little mountains out there because the mangroves are like twice as tall. And when you go under there, there's actually, the carbon barrel isn't as rich in those locations because it does have more fresh water, it has more oxygenation occurring. So it's one of those weird things where, like, the stressful environment, the more anoxic, the less exchange, the more it actually buries. And so one of the things we've seen, like even in South Florida, is that you can end up, it's kind of a balance between supplying and subtracting. And so, like, if you look at like a traditional, like kind of a bermed fringe versus an interior, the litter is going to accumulate more on the interior. There's going to be less exchange. And so you actually end up with higher burial rates farther from the shoreline than you would at the shoreline. Yeah, it's a fun conversation. It's not simple.
All right. Do we have any other questions?
No, you're good.
There's
a question in the chat box. Yeah.
Yeah, I was going. Yeah. All right. So this is from Zachary Faza, architecture grad here. I've been exploring architecture as a means to add to ecological health rather than just striving for sustainability. Has there been discussion of restoration being integrated with human development? If you were to undertake such a task, what would you prioritize for restoration, and how would you design this? Would love to talk more about these ideas if you think there is potential for development. Smiley face.
That's great. Yeah. So first of all, let me add in responding to that and just throw this out there. Anybody who wants to talk more about this, I'd love to have more conversations, and I'm happy to take people in the field or work with you in the lab. There's lots of stuff I'm very interested in helping out with projects on this. In terms of the thing to focus on, what's interesting with restoration is if you watch for the last 10 to 20 years, it's really tempting to pull people out to go plant mangroves, to go take propagules and go put holes in the beach and pop them in there. But the overwhelming lesson globally is that if mangroves are not there now, there's an ecological reason. And almost in every case, that phrase I used, the get the water right here on this slide, is the one we have to think about. So it's hydrology. If the hydrology is right, the restoration will be successful, or it's got much greater chance of being successful. The other thing I'll throw in that's just kind of like a little bit of a hook here that's kind of funny. Down south, like in Tampa, when you're doing a restoration and you want it to be a mangrove restoration, the best way to ensure success is to go out and plant Spartina, and then it'll naturally recruit mangroves, and within 5 years, you'll have mangroves growing. So there's different things in different areas, but the hydrologies are I think probably the number one. And I can share, if you want to follow up or shoot me an email, I can share some papers with you that do some really cool things, looking at how there's one that even use sort of like a medical metaphor that talk about a heart attack, and how from a human health standpoint, a heart attack doesn't just happen overnight. It's the kind of thing, poor health slowly happens and then the heart attack hits. And they talk about hydrology really mimicking that it's a slow change. The mangroves will hang on for as long as they can, but then it's, a tipping point, a storm or something like that will drive the collapse. And so restoration has to account for that as well.
All right, do we have any other questions? Okay, go in. Okay.
I have a general question here. I don't know whether you'll attempt to answer it. In the past decade also, there were mitigation measures that were actually kind of implemented globally to try to, to control carbon. And that was actually something which maybe was expected to arrest the sea level rise. But I'm wondering whether these measures have ever had any impact so far. Has any research been done in that area to show whether there's been positive impact to actually towards the, arresting the sea level rise? Those efforts, yeah.
Well, I mean, that last part, arresting sea level rise, I think from what I understand of that, there's enough inertia in the system. From what I understand, I think we could stop CO2 emissions today and sea level rise is still going to occur. There's a lot of inertia in that system, just in terms of the glacial melt that's occurring. But in terms of like impacts to global CO2, I think the biggest thing, we could talk about this offline too. I'd love to follow up with you. Blue carbon's kind of interesting because what they're really worried about isn't so much of the sequestration as the stocks that are there that are vulnerable. So the idea of all that carbon that's stored, if you lose, again, my idea, if you lose the plants, you lose the ecosystem, you lose all the soil and the carbon. And so it's not so much whether we're going to draw down more carbon, it's the concern that if we lose these wetlands, we're going to release all the carbon back, and it's going to actually be, a negative impact on climate. So it's trying to preserve and protect.
All right. Thank you.
Thank you. Okay.